Hi, everybody. Very good. So, the homework assignment, next homework is due on Thursday. We'll have our problem session afterwards with Charlie. And Kirk switches to the first assignment. We'll post it so you can get it there. All right. So, last time we started our foray into the heart of the subject, thinking about getting towards the notion of quantum coherence in matter. And the way we're doing that to start is to think about the situation looking at absorption and emission of light by atoms. And what we discussed last time is that when we have some kind of atom with some energy level structure, and when the applied radiation, when its frequency is sufficiently close to resonance, such that the detuning from resonance is small compared to the splitting between any other levels. And if there are near degenerate levels, the applied interaction just doesn't couple to those levels. For example, if there are selection rules based on polarization of the light. So when that is the case, we can then restrict our attention solely to these two discrete energy levels. And all of the dynamics of our atom are then described in a Hilbert space that's two-dimensional. Okay? And that means that, for example, any state vector that describes the atom is just restricted to this subspace, would be generally some superposition of ground and excited states. All right? So this is a very important problem. What it tells us is that we can understand a lot about the interaction, for example, of light and atoms by looking at the mathematics associated with the 2D Hilbert space. And so we're getting that stuff under our belts here. We have our 2D Hilbert space. And every 2D Hilbert space is isomorphic to the description of a spin 1/2 particle. Okay? So we have our spin 1/2 particle, which has some canonical basis, some standard basis, typically spin up and spin down along the z-axis, the chosen quantization axis. And in describing that, we rely on certain notions related to the angular momentum algebra. So in particular, we have a spin angular momentum vector, which satisfies the usual spin commutation or angular momentum commutation relations. There is a rescaling that gets rid of all these factors, our h bars and factors of 2, the Pauli matrices. So spin up is +1 eigenstate, and spin down is the -1 eigenstate with respect to this axis. And then we have spin raising and lowering operators, sigma plus and sigma minus. And the spin components along x and y, scaled in this way, sigma x and sigma y, are related to the raising and lowering operators in that way, right? And there's all kinds of algebra. We have to get it under our belts. So the Pauli matrices, if you multiply them together, bless you, if they are, if they're different, then you get one of the other Pauli matrices with some factor, plus or minus 2i. And if they're the same, well, then you get it back. Okay? And so that means that if you square any of the Pauli operators, you get the identity, the 2 by 2 identity. These operators or matrices are traceless, the sum of their eigenvalues sum to 0, and they're orthogonal. Orthogonal with respect to the trace inner product, as we discussed last time. Yep.
Should the sigma J be there?
No, it shouldn't. Sorry. That's the identity. Pardon me. That's screwed up. Yeah. Right. So, yeah, sorry. Right. Right. So when you take the trace of this is traceless, and the trace of the identity is 2. That's why that factor of 2 is because it's the one, it's the identity matrix in 2D. Right. And furthermore, what we discussed based on this factoid is that any operator, or matrix if you like, in a matrix representation, in a 2D Hilbert space can be always expressed as some amount of identity, some amount of sigma x, some amount of sigma y, and some amount of sigma z, where these coefficients, a0, ax, ay, and az, are the projection of the operator or matrix onto the direction in matrix space defined by either the identity sigma x, sigma y, and sigma z. Okay? All right. So, what we were discussing at the end of lecture last time was, in particular, looking at unitary operators. On 2D Hilbert space. And any such unitary operator can be written as e to the minus I A, where this is some Hermitian operator. And any such operator can be broken up in the manner that we described over there, which is some overall phase factor, e to the minus I A dot sigma, where this is sigma x, sigma y, and sigma z, right? Now, quick question for you guys. Here I'm talking about a Hermitian operator, right? But this result is general. This is always true. Doesn't matter whether A was a Hermitian or not. So what restriction, the fact that this is Hermitian, what does that say about these coefficients? They must be real, because when I conjugate this, these guys are Hermitian, and these go to their complex conjugates. But if this is going to equal a dagger, it must be the case that these are real numbers, okay? So the fact that A is Hermitian means that A0 and the vector A is real, which means that this is just some phase, where phi is some real phase. And this is over 2, the way I bring it over there. If I write this, I can write this e to the minus I theta over 2 n hat dot sigma, where I've written A as having a magnitude capital theta, and this is the direction of that vector. Okay? Just a definition. And we recognize that, as we discussed last time, as the rotation operator, right? That is to say, I can rewrite this by multiplying top and bottom by h bar. Right? And this is nothing more than eta minus I theta n hat dot s over h bar, which we recognize as the rotation operator. It is the thing that carries out physical rotations in space, three-dimensional space. Angular momentum is the generator of rotations. Okay? So what this tells me, if I call this thing some rotation operator, D, about some axis, so now I think about this is some axis, and this is some angle of rotation. That is to say, I have some axis n, and if I have the spin vector, it'll rotate by an angle theta around that axis according to the right-hand rule. So if I take this operator and I conjugate, I do a unitary transformation on any component of spin, that the result is a rotation matrix acting on that spin. So this is a rotation matrix in 3D. That's what it means to say that this generates rotations. It says that this vector is now a rotated vector. Its components are rotated. Okay? So, for example, I can obtain if I have some vector along the z-axis, say this is the x-axis, this is the y-axis, I can obtain a vector that is pointing in an arbitrary direction, specified by polar angles theta and phi, where phi is the angle relative to the x-axis and theta is the angle relative to the z-axis, through a series of rotations. If I first rotate this vector around the y-axis, by theta, and then rotate it around the z-axis by phi, I end up with a vector that points in the direction E sub n, right? If E sub n is some arbitrary direction that's specified by theta and phi. Okay? Now, I talked about this rotation, sort of thought about from the Heisenberg picture, if you like, how it transforms the operators. But I can also, and do also think about that as how it applies to a state. So if I have a spin along some axis, let's say it's a spin along the z-axis, and I apply this series of rotations to it. So first I rotate it around the y-axis, by the angle theta, and then I rotate it around the z-axis by the angle phi, then this is spin up along that direction. So the action of the rotation operator is to rotate the direction of spin. So that here it was spin up along z, then it's spin up along this funny direction, and now it's spin up along that direction. Is that clear? Now, one thing, of course, when coming back over here for a moment, is that as we remember, there is this way in which we can take this general rotation operator around an arbitrary axis and rewrite it in some combination of the identity and the Pauli operators, as any operator can be decomposed. Okay, so this is capital theta. That's a general expression when I have spin 1/2. This is not true for anything other than things such that the Pauli's or whatever this thing has to square to the identity. If it doesn't square to the identity, this is not the expression. So for spin 1, I can't do that. Okay? Keep that in mind. Okay, and so now we can write that out here. This is cosine theta over 2 times the identity minus I sine theta over 2 sigma y. That's this guy. And I'll leave this as either minus I phi over 2 sigma z. Acting on spin up along z. Right? So that's equal to the identity acting on sigma from this is spin up along z. And sigma y, well, it's still over here. When I act sigma y on spin up along z, what do I get? So this guy, I get this minus sign, I can bring it up, this turns it, right? So that minus sign cancels that minus sign, the I cancels the I, and this turns spin up to spin down. So this becomes either the minus I phi over 2 sigma z spin cosine of theta over 2 spin up along z minus I sine theta over 2, well, get rid of that, plus spin down along z. Right? And then I can take this operator and act it on each of these. And sigma z acting on that gives me plus 1. And sigma z acting on that gives me minus 1. And I can do it in the exponent, that's fine. So that becomes e to the minus I phi over 2 cos theta over 2 spin up along z plus e to the plus I phi over 2 sine theta over 2 spin down along z. All right? So this, as we discussed at the problem session, for those of you who were there, so this is a review of that, but what the heck, tells us the following very important fact. I can, up to an overall phase, so let me factor out that. You see how I cheated? I factored out as e to the minus I phi over 2, and then that becomes that. And now this overall phase, I don't care. Negligible. Doesn't matter. Tells us the following very important result. A spin pointing up along the direction theta phi. So these are the usual polar angles of spherical coordinates that everyone knows, and everyone forgets what their undergraduate mathematician told them about theta and phi. You forget about that. This is theta and phi forever and a day. All right? That this is the directions, theta and phi, that if you have a spin up pointing along that direction, it can be expressed always as a superposition of up and down along any direction, in particular along the z-axis, right? So it says spin up along this direction is equal to cosine theta over 2, spin up along z, plus e to the I phi sine theta over 2, spin down along z. That's an important result. Okay? So, for example, spin up along x. The x direction is the direction where theta is pi over 2 and phi is 0, right? So that is cosine pi over 4 and sine pi over 4, which are each 1 over root 2. What about spin up along minus x? Well, that's the direction where theta is pi over 2 and phi is pi. Which is equal to 1 over root 2, the same thing, but now this is e to the I pi, which is minus 1. Which is also known as spin down along x. All right? So it's always the case that spin up along minus the direction is equal to spin down along that direction. Spin up along minus z is spin down along z. Right? What about spin up and spin down along y? Spin up along y, what are theta and phi in that case? Theta is,
I over 2.
yeah, and phi is pi over 2 as well. So that is equal to 1 over root 2 spin up along z plus I spin down. Right? Note, spin up along x is not orthogonal to spin up along y. What is the inner product between those two? Well, I just have to take the inner product of this with this, right?
1 plus I over 2.
Yeah. 1 plus I over 2. Right? Which is equal to 1 over root 2 times e to the I pi over 4. Right? Of course, that means that there's a 50% probability of finding spin up along x if the state is initially prepared in spin up along y. Right? The thing that's orthogonal to spin up along y is spin down along y. So there is now, here comes the rub. The confusion between what's going on in three-dimensional space and what's going on in Hilbert space. So we have the sphere. Right? Here it is. This is a three-dimensional sphere, a three-dimensional space. Okay? And there is here is x, y, and z. And I can talk about an arbitrary direction in three-dimensional space by these polar angles. And there's some three-dimensional vector E sub n that corresponds to that. And this is in one-to-one correspondence with spin up along some direction. Okay? So directions in physical space, here we are, our physical space, three-dimensional space, are directions of you know, I can produce a spin up along that direction. However, this space has another interpretation completely. It's called Hilbert space. So one of the things you've done in your, you've already done it, I hope, your first part of your first problem of your next problem set, which shows that every state, if I have a state which is in this two-dimensional Hilbert space, it is in one-to-one correspondence with spin up along some direction. Which means this space, the surface of this sphere, is itself a way of representing Hilbert space. It is what we call the block sphere. It's a very important construct, where the North Pole is spin up along z, and the South Pole is spin down along z. This is spin up along x, and this is spin down along x. Well, on this part of the sphere, right on that point, is spin up along y. And on this part of the sphere, right here, is spin down along y. This is spin up along that direction, and then there's an antipodal point, which is spin down along that direction. Okay? Now, notice states in Hilbert space, so I should say antipodal are orthogonal. That is to say, the North Pole of the block sphere is orthogonal to the South Pole. This point on the equator is orthogonal to this point on the equator, as opposed to, so you have to double the angles. Right? But what it says is that I can express, just thinking about this, any point on the sphere is some superposition of this and this, according to this important formula. What it says is that the angle relative to the z-axis, which you might call the mixing angle, sometimes it's known as that. That is to say, it tells me, it really should be called the superposition angle, but it's called, it tells us how big the superposition is, what fraction of the probability amplitude is this, and what fraction is that. And the phi angle tells us what the relative phase is between the two. Okay. Yes?
Is there a geometric or a visual rule on how we add vectors? Because before, so in normal 3D space, if you give me two vectors, I can do the parallelogram rule and say, oh, this is where the other vector would be.
Sure. So you can ask if I made a superposition. There is indeed. It's an interesting question. I mean, suppose I took two vectors and I added them. I have to, of course, normalize them. right? So I have some alpha this and beta that. How do I think about that in terms of this has got to be spin up along some other direction? Yeah, that's a bit homework problem. We'll see some of the more of that. You can look at some of that geometry in your work another way. There isn't a simple relation here, but we'll see a different one that is very simple when we start talking not about superpositions, but statistical mixtures. We'll come back to that. This doesn't have a very simple picture. What we see here, because there is a one-to-one correspondence between those, what we would say is every point on this space is so there is a one-to-one mapping between states up to an overall, it's not really one-to-one, up to an overall phase. It's the overall phase, doesn't matter. Up to an overall phase, this is in one-to-one correspondence with the direction of space. And that vector is known as the block vector, which I'm going to call in this class, we're going to call it instead of E sub n, because we're going to not necessarily talk only about unit vectors, we'll call it Q. Okay? And generally speaking, if I'm given a state, the block vector Q is the expected value of the vector of Pali matrices. So you give me a state, I can give you a block vector. You give me a block vector, I know its direction, I can find the state. All right. Any questions about that? It's a very important construct, and we'll come back to it. I guess there's one last thing I want to say before I move on, which is, of course, this is true regardless of whether this was spin. I mean, part of the point here is that all 2D open spaces are isomorphic. So I could instead think about this as the excited state of the atom and the ground state that are connected by my, then what is this state? It's excited plus ground, because that's what we said, spin up along x is that, right? So this is the superposition excited plus ground over root 2. It sits right over here on the block sphere. What is this state? No, sitting over there somewhere. This is excited plus I ground over root 2. Okay? Every point on the equator of the block sphere where theta is pi over 2 is a 50-50 superposition, equal amounts of excited and ground. The difference between them is the phase. So this state is the orthogonal state excited minus ground over root 2. And as I change the angle, it gets closer and closer to all being all excited or all ground, and everything in between. In your homework, you have another example. The example of the Poincare sphere, where we think about polarization states of light. Of course, that mathematics was developed by Poincare well before quantum mechanics. It has nothing to do with quantum mechanics per se. It has to do with the algebra of two-dimensional vector spaces with complex scalars. And so instead of thinking about them as probability amplitudes, they're electric fields. But they could also be the probability amplitudes of a photon. So this might be right-hand circular and this left-hand circular. This horizontal, this vertical. This 45 degrees, this minus 45 degrees. Everything between is elliptically polarized. everything on the equator is horizontally polarized. And that means it's linearly polarized with a different angle depending on the relative phase of right versus left. Okay? So this is an extremely important construct, and what it says is it doesn't matter what two orthogonal states, these could be any two orthogonal states in Hilbert space, I can construct a block sphere always relative to them. They could be two different histories of the universe that are orthogonal. All right, very good. All right, so let us continue then, and let's talk about dynamics in more detail. And what we want to talk about, what we talked about a few lectures ago was Lorentz oscillator model for absorption and emission based on a classical model of the charge on the spring. Now we want to talk about the quantum mechanical model. Now that we have some of this mathematics under our belts, we can continue on. We're talking now about absorption and emission of light. With a little app. All right. Now, when we do that, as we've discussed, if we are restricting our attention solely to the two levels, well, then we know the form of the Hamiltonian, because there's only one possible form there is for a two-dimensional Hilbert space. My Hamiltonian must be of the form some amount of the identity and some amount of the Pauli matrices. That's all there is. Now, these coefficients might be time dependent, but other than that, there's nothing else. Which is, of course, a Hamiltonian we recognize. This overall constant, I don't care. It's the same for the two states, I can take it out. This is related to, this is the Hamiltonian for a spin 1/2 particle in a magnetic field. Let me not call that B because I don't want to confuse it yet. We'll just come back and we can call it as we did before. Right, that's the form we had before. Why is that? What is the Hamiltonian for a spin in a magnetic field? Minus mu dot B. Thank you very much. Right? That's the Hamiltonian associated with the spin in a magnetic field. And this magnetic dipole moment is proportional to the spin angular momentum through a proportionality constant that we call the gyromagnetic ratio. Okay. So, for an electron, just to think of an example of an actual spin 1/2 particle, this would equal minus 2 the Bohr magneton, the spin angular temporality. Right, so in this case, gamma is minus 2 the Bohr magneton over h bar. Now I want to emphasize something here. I'm talking about this in relation to the dynamics of a physical spin in a physical magnetic field. However, what we're doing is going to connect this abstractly to a pseudo-spin, where up and down are excited and ground, in a pseudo-magnetic field, which has nothing to do with the physical magnetic field or the physical spin. It is a mathematical mapping between these two levels, E and G, and spin up and spin down. Okay, so keep that in mind. But it's convenient because it gets so confusing to keep around this damn minus sign over here. And I've done back and forth after 10 years of teaching this course how to absorb minus sign is to make the gyro magnetic ratio negative. Okay? And think about this with the electron. All right, so we will rewrite this then as plugging that in. So this is equal to minus gamma times S over H bar dotted into B, which is equal to minus gamma sigma B dotted into sigma over 2. Right? Rewriting the Pauli, writing the Pauli operators. Okay. This is an energy, so this has the units of energy. I'm going to call this thing here H bar So H bar omega naught is minus gamma. Yeah.
Something weird happened. We went from, there is a gamma and S, but you only get H bar when you transform gamma into mu B, but you have H bar there already. Do you get what I'm saying?
I do. Yeah. You're right. There should be, some gamma here, H bar here, and the H bar should be here. And so this is a frequency, not an energy. You're correct. Thank you. Okay, so omega naught. So let's look at this. In a specific example. Let's say we call B as some magnetic field in the Z direction. Okay. So in that case, the Hamiltonian, the magnetic Hamiltonian, is equal to H bar omega naught over 2 sigma Z. Well, omega naught is minus gamma B, positive naught. So I'm taking gamma B negative. All right? So what are the eigenstates of this Hamiltonian? That's the eigenvalues, right? And the eigenvectors are spin up and spin down. So the eigenvectors spin up along the magnetic field and spin down along the magnetic field. Okay? And because of the fact it's minus sign, when it's aligned, it has higher energy than when it's anti-aligned. Much nicer that way. And this energy is plus h bar omega naught over 2. This is 0 energy, and this is minus h bar omega naught over 2. And the splitting between them is h bar omega naught, where this is omega naught. Okay? So those are the eigenstates of the system. If I prepare the system in a state that is not an eigenstate of the system, what will happen? Well, it will evolve in time. It will evolve in time according to the time-dependent Schrödinger equation, right? So if I have some arbitrary state at time t equals 0, the state at a later time will be equal to whatever the time evolution operator is acting on the state. Right? That's the solution to the time-dependent Schrödinger equation. And what is that, u of t? Well, by given this Hamiltonian with this magnetic field, it's a constant magnetic field, so we can just exponentiate the Hamiltonian and apply it to our state. So what is this equal to? It's equal to e to the minus I, plugging in for this is this Hamiltonian, omega naught t over 2 sigma z. What is that operator? That's a rotation operator. I mean, we know that. Every unitary operator in 2D Hilbert space is a rotation operator. That's all there is. And what does it do? It rotates around the z-axis by what angle? Omega naught t, right? Not omega naught t over 2, but omega naught t. Thank you, Adrian. Right, because it's theta over 2. So that says if I have a magnetic field in the z direction, and I start a spin in some arbitrary direction, it will precess around the z-axis at an angular rate omega. That is what we would call Larmor precession. Okay, so the spin precesses around the z-axis by the frequency omega naught t. Omega naught t. Where omega naught is this splitting that's set by p. All right, so it precesses. Now, what we want to talk about is the notion of spin resonance. So now what I want to do is I want to flip the spin. Make it go from near spin up, or spin up along z, to spin down along z, right? Now, from the quantum mechanical point of view, we know how to do that, right? From the quantum mechanical point of view, if I want to go from this state to this state, or from this state to this state, what I do is I apply a field that interacts with the spin, that is resonant, that oscillates near to this frequency, and causes, if I want to go from spin down to spin up, it would absorb, right? Or it could stimulate, emit, go from up to down. So spin resonance says the following thing. Apply a magnetic field that couples spin up along Z to spin down along Z, which oscillates at omega near omega naught. That's the phenomenon of resonance. Okay? So if I apply a field which has a frequency near to that, then I can get it to go from spin down to spin up, or vice versa, right? So how would I describe that quantum mechanically? Well, quantum mechanically, I would say I have some interaction Hamiltonian, which of course we'll be able to write down because this all has the same form. But it would oscillate at frequency omega. And we would have a part that would go like e to the minus I omega t, and a part that will go as like e to the plus I omega t, and we call those the positive and negative frequency components. Right? Now, if you have studied absorption emission, the first thing you might do if you wanted to ask, what is the rate of transition between here and here? I might say I'll use Fermi's golden rule, right? Fermi's golden rule says something that the rate of absorption, say going from spin down to spin up, well, that's given by the matrix element for absorption. Some factors here. And then there's some density of states evaluated at the resonance frequency. This is the usual thing you'll see in a standard textbook talking about absorption emission. But this picture isn't really the whole story, and it's maybe not even the relevant story here. This notion of the density of states, what the heck am I even talking about here? What density of what states? What are we talking about? I have two levels, right? So this is a kind of incoherent picture of absorption and emission, when you might be learning about your laser physics course, where there's incoherent pumping with a flash lamp or something like that. We're not talking about that here. What we're talking about is coherent laser light interacting with resonant levels that are very sharp, that have definite energies. And this picture of Fermi's golden rule says nothing. It says that it's something I go from here to here in some kind of jump. I absorb a photon, or I emit a photon. But it doesn't say anything about the dynamics of how I got there by the time-dependent Schrodinger equation. I mean, this whole Fermi's golden rule kind of, there's some time-dependent Schrodinger equation in between. But how did that work? So we want to look at this more carefully. Let's talk about this problem. Where now, let's think about what our interaction Hamiltonian is. The one that's going to couple spin up to spin down along Z. kind of physical force would do that?
Big magnetic field in the z direction is constant and an oscillating one spinning around.
So I have to have a magnetic field in the x direction or the y direction, something perpendicular to z, which causes a torque of the magnetic field. So I need a magnetic field in the direction perpendicular to the z-axis. All right? Right. And as Keith suggested, because we've studied this before, there's an easy way to see how we can for sure get a resonant interaction. Suppose I have a magnetic field in the xy plane that is rotating in the xy plane. So here's my B perp. This thing, in the absence of B perp, is Larmor processing, right? It's Larmor processing at frequency omega naught. Now I apply this transverse field. If this was not rotating, it would process around this axis. At what frequency?
And times B perp.
Yeah, so there would be some omega, I'll call it minus gamma times B perp, right? If it were static. But of course it's rotating around. But if I make this thing rotate around at frequency omega naught, then it's perfectly resonant. And if it's close enough, it'll do close enough to the job. So if I have a magnetic field that is rotating at near to frequency in the xy plane, that is rotating at frequency omega, near to omega naught, it is going to cause this spin to process along it and go from near spin up along Z to spin down along Z. Notice, this field can be tiny in magnitude compared to that field and have this huge effect to cause this thing to go from spin up along Z to spin down along Z. As long as it rotates at or quite close to omega naught. Yes, sir?
What does resonance mean in this case?
Resonance means that you're driving it. In this case, you're rotating the field at a frequency near to this frequency. They have to be resonant with one. They have to be near to one another.
So what I meant to ask is, maybe I should phrase it differently, what does resonance do?
So let's ask the following question. Suppose that omega was not anywhere close to omega naught. In fact, I wasn't resonant. I wasn't near resonance whatsoever. What would be the effect of this small magnetic field on this processing spin?
Wiggle it?
It would wiggle it a little bit. Every once in a while, I'd give it a tiny kick, but this thing's whipping around. And every once in a while, it's fly, it's just gonna bother you. Give you a tiny little kick, but it's just gonna wobble a little bit, but it's gonna be kind of fixed. But now, if I'm this little fly, but I go exactly with you, my force collects, and I make a big effect. I pull this thing all the way from spin up to spin down. Even though I'm a tiny torque, the fact that I'm being applied near resonance means that my force accumulates in a big way and gets the spin to go from up to down.
And it'll stay down until you remove that B?
Well, no, then it'll process all the way back up.
Okay.
You see? It keeps going, it'll process like this. So this whole spin, what's happening is this guy is going around the z-axis at frequency omega naught at the same time that it's processing around this axis at this frequency.
So how does the overall vector look when it's doing these two very different things?
Well, I think the thing to think about is this. Let's say I'm in the rotating frame, the frame rotating around this. It rotates around the perp like this. And now take this thing and rotate it at the same time at frequency omega naught. You do that in your head. That's what it's doing, right? It's really not so important to get that. Well, the picture is here. In the rotating frame, it's doing this. And then the whole thing is spinning around at frequency omega naught. But that's the magic of resonance. The magic of resonance is that even though the applied force is a perturbation, is a tiny force, its cumulative effect is huge. Okay? So, how can we describe that? Well, in this case, we can describe that exactly. So, what is my interaction Hamiltonian? So I'm going to apply a magnetic field. My magnetic field is going to be in the direction perpendicular to the z-axis. It's going to have an x component and a y component. And it's going to be rotating. So it has an x component and a y component. And we're going to make them the same. So it's a now, in principle, it could start anywhere at time t equals 0 as determined by this phase, right? So phi there is just where it is pointing at time t equals 0, but that's not going to be important for the resonant phenomenon, but we'll come back to why I keep that phase in a moment. Okay? So this is a vector rotating in the xy plane at frequency omega. Okay? And this is its amplitude. This is a function of time. My interaction Hamiltonian as a function of time is then equal to minus mu dot d perp as a function of time, which is equal to minus gamma h bar sigma over 2 dot d perp as a function of time, which is equal to minus gamma d perp times h bar over 2 cosine omega t minus phi sigma x plus sine omega t minus phi sigma y. Okay? We'll call this frequency capital omega. That's the precession frequency around the perpendicular axis. All right? So, what do we got here? Let's rewrite sigma x and sigma y in terms of sigma plus and sigma minus. So this then says that the interaction Hamiltonian as a function of time is equal to h bar capital omega over 2. Let me write it up above there. and now I'll express sigma x is equal to sigma plus plus sigma minus, and this was sigma x minus sigma minus over I. Put it all together, and this is what you get. E to the minus I omega t e to the I5 sigma plus e to the plus I omega t e to the minus I sigma minus. This has the expected form, the form that I said it must have. It has a component that went like e to the minus I omega t, and a component that went like e to the plus I omega t. Here they are. The component that goes like e to the minus I omega t is associated with absorption, going from spin down to spin up. There is a component which is related to emission, which is the conjugate term, which is sigma minus, which takes spin up to spin down. All right? So now we have to solve the time-dependent Schrodinger equation. Right? We want to solve the time-dependent Schrodinger equation where we have my total Hamiltonian is H naught plus my interaction Hamiltonian as a function of time, where H naught is the one we just had over here. It's what I call H max there. So let's see. The agent is here. Now, question. Can I just say that this is the time evolution operator. I just exponentiate the Hamiltonian and then apply that to the state, and I'll get that precessive spin. Is that okay? No, that's not okay. That's not okay. You can't just exponentiate a time-dependent Hamiltonian because it's time-dependent. Well, maybe I should integrate the t dt from 0 to t. That looks better. Yeah, exactly. Excellent. You can't do that either. Because the Hamiltonian at different times doesn't commute with itself. H of t does not commute with h at a different time. You could see that right away because at time t equals 0, the interaction Hamiltonian is along one direction. Say phi was 0, it would be along the x direction. And then later it would be along the y direction. And sigma x and sigma y don't commute. So when the Hamiltonian doesn't commute with itself at different times, you can't, it's so ugly, solving the time for the time evolution operator. Barely, it can't be done. There is no closed form solution, which is why we resort to perturbation theory on when it's a good approximation. However, the big however, in this case, we can play a trick that we see from this picture, which is that this magnetic field, which is why the time dependent, why the Hamiltonian time dependent is rotating around. If I go into the frame co-rotating with the magnetic field, well, then the magnetic field isn't moving. It's a static magnetic field. So if I go into the frame co-moving with the magnetic field, not co-rotating with the spin, but co-rotating with the magnetic field, then the field is static. And when we have a static magnetic field, we know how to solve the problem. It just precesses around the static magnetic field. So we need to go into a co-rotating frame. in that reference frame, the magnetic field will be constant. And when the magnetic field is constant, the Hamiltonian is constant. And when the Hamiltonian is constant, Haydn's happy. All right? You should be too. So how do we do that in quantum mechanics? Well, moving into a co-rotating frame or moving to a different reference frame is equivalent to performing a unitary transformation. In this case, moving into a rotating frame means performing a rotation, rotating the system with the magnetic field. Okay? So, I have a unitary transformation into rotating frame. I want to co-rotate with the, so this omega is the frequency of rotating ether. It's not omega naught. They're near one another, but I want to go into the frame that's rotating with the magnetic field, so the magnetic field is static. Yes, sir.
So if you have like a spin one particle, would the rotating operator like that look the same, or would like a different?
It would look, so remember what generally would look like e to the minus I omega t spin over h bar. That's, I mean, in this case, sig and c. That's what it would generally look like, right? In the specific case, it's spin 1/2, then we wrote this as h bar over 2 times the Pauli, which is where that comes from. So that would be the general form in E. Because it's a rotation around the z-axis. All right, excellent. So how do we apply that in the quantum mechanics? Well, what it says is that we're going to put this rotation, we're going to transform in the following way. So transform to the rotating frame. We define in the rotating frame, we have a new state. You got to take out that rotating field out of the Schrodinger picture. So this is my state in the Schrodinger picture. I want to know how this state evolves as a function of time. Well, according to this, is equal to the derivative of this u dagger psi plus u dagger d by dt of psi. This is given over here. It's equal to, let me multiply because it's making it easier for us to see what's going on. Multiplied by h bar over minus psi, h bar over minus psi, h bar over minus psi. Taking that derivative, I get minus h bar omega sigma z u r f dagger on psi. what is this? The derivative of psi with respect to t. Well, multiplied by h bar over mine, that's the Schrodinger equation. That's equal to the Hamiltonian, which is h naught plus h int of t. Okay, that's the time-dependent Schrodinger equation. The derivative of the state vector is proportional to the Hamiltonian, right? Remember the time-dependent Schrodinger equation? So now let me multiply this by u dagger u. I can always do that because, I'm sorry, the other way around. This should have been a u dagger, right? And that's a u dagger. Put it all together, and this is what we get. So, the derivative of my state, the rate of change of psi in the rotating frame, is equal to h naught plus u dagger rotating frame h int u rotating frame, h bar over minus I. Okay. So this is the new Hamiltonian. Oh, I forgot what happened to that piece, minus h bar omega. H naught minus h bar omega sigma z plus this. Let's put this together and then we'll quit and explain what we're talking about here. So I get h naught over here. This becomes minus h bar omega minus omega naught sigma z. I guess this should have been over 2, huh? I forgot the over 2 when I took the derivative. Over 2. What about this thing? Well, I got to conjugate this, and I got to conjugate that. What it does, this becomes e to the plus I omega t, cancels that. This becomes e to the minus I omega t, cancels that. And this, my friends, is the important point that we'll be stopping at right now. What do we see here? This is the Hamiltonian in the rotating frame. And what is its form? Well, this is of the form this is of the form h bar omega times some total frequency over 2 dotted into sigma. That is the form of the Hamiltonian in the rotating frame. Let's look at the case where we're right on resonance. When I'm right on resonance, this is equivalent to a magnetic field along, I guess plus along the direction phi. So in other words, if we had like sphere is gone, sorry. We have this rotating frame, rotating magnetic field. If I'm in that, it's like there's a magnetic field along that direction. And it's just going to process around that axis by this frequency. When I'm off resonance, there's an additional effect which is related to the detuning. How far am I from resonance? But the net effect is a rotation around a static magnetic field. And we will pick that up next time. See you then.